Welcome to my lecture on linear regression. Um, so as you guessed, the word linear suggests that there's a line in it, and so we write down the equation y equals mx plus b. But because of the statistics, our information isn't perfect. So there's going to be random error in our observations, epsilon. And we assume that epsilon is a normal distribution with mean 0 and constant variance. Okay. We also assume that our observations are independent. Okay, and by an observation, I really mean a pair xi, yi. Okay, the random part is yi. Xi is assumed to be just a value that's taken, so it's not assumed to have randomness. In reality, that may not be true, but the way we treat it is that x is not random. X is the given quantity. Okay. Okay. And in some of your homeworks, I refer to epsilon. This can sometimes be called the noise or the error. Okay, because it's what makes our data imperfect. Okay. Then, of course, our last assumption is that observations are identically distributed. So, and one other thing to note is that I call the mx plus b, so it's the true equation, but because we don't know what the true equation is, we must estimate them. And that's the whole theme of linear regression, is that we don't know the slope or the intercept, so we have to estimate them. Okay, and this whole lecture is about how do we estimate them. Okay, so I'm going to go, there are several ways to estimate them. The most common and the one used in your book is called least squares estimate. However, You can also use the maximum likelihood estimator if you would prefer, and they give you exactly the same results. Okay. So least squares estimate. Okay. The least squares estimate says we want to minimize the square of the error. And I should add one more word, sum of squares of the error. Okay. So if I'm insisting that my equation have this form y equals mx plus b, and I have an observation yi, that's my observed value, minus the predicted value. So my error is going to be observed minus predicted. So why don't I back up for a second? So what I'm calling error that's going to be the observed minus the predicted. My observed value, that's the observation yi. I observed that data. What I predict is if I have an input x, I predict that its output is going to be m times xi plus b. So that is the error term right here. Okay, and I want to minimize, so my goal is to minimize the sum of the squares. So sum of the errors is going to be the summation from I equals 1 to n, and I'm probably going to drop the subscripts. The error is going to be my observed yi minus mxi plus b, quantity squared. Okay, this happens to be a function of m and b. So I want to minimize that. I can use calculus. Since this is a nice and differentiable function, I'm just going to take the derivative of the least squares function with respect to b, and I'm also going to take it with respect to m, but I'll do b first. So this will be bring the exponent down, summation of twice times yi minus mxi minus b. Now to the first power, multiply by the derivative of the inside. That's the derivative with respect to b is minus 1. Set that equal to 0. I'm going to divide by negative 2, and I'm going to get summation of yi, and I'm going to apply the properties of summation minus m times the summation of xi minus the summation of b equals 0. Okay. Now, since the sum is from I equals 1 to n, this last part here, because it's a constant, just becomes minus n times b equals 0. This is going to be minus m times summation of xi, and it's going to be summation of yi. Okay, my goal is to solve for b. So divide by n and move b to the other side gives me that b is going to be summation of yi over n minus m times summation of xi over n. Since these are sums from 1 to n, I just get y bar minus m times x bar. And that's how I estimate the value of b. So notice I have two unknowns, m and b, and right now I just have one equation. That was when I took the derivative with respect to b. So now I'm going to take the derivative with respect to m. So dl, derivative of the least squares with respect to m. Again, I bring the exponent down, so it's twice yi minus mxi minus b. Now the derivative with respect to m of the inside is just going to be minus xi. And I set that equal to 0. Excuse me. And I divide by minus 2. That gives me, and then distribute or FOIL the minus xi. And that's going to give me the summation of yixi minus m times xi squared minus b times xi equals 0. Then I'm just going to take the sum of both, applying the properties of sums like we did before. And I'm going to get summation of yi xi minus m times summation of xi squared minus b times summation of xi equals 0. These are equations that we have. Now I have two equations, two variables, m and b, and I need to solve for m. So I'm going to substitute that b is going to be y bar minus m times x bar into the equation. And I'm going to get summation of yi times xi minus m times summation of xi squared. Then I have a negative b, so minus y bar minus mx bar times summation of xi equals 0. And I'm just going to solve for m, so I'm going to simplify this equation. So summation of yi times xi minus m times summation of xi. And then I'm going to get minus y bar times summation of xi. Okay, and that little bit at the end is a little bit unclear, so I'll just put the equals 0 part on this side. Okay, since it's equivalent. Minus y bar times summation of x bar plus m times x bar times summation of xi equals 0. Okay, and that's the equation that we have. So I can group these two terms that have m. So the two terms that have m are this one, and I'll move everything else to the other side. Okay. So on one side, I'll have summation of yi times xi minus y bar times summation of xi equals m times, and by the way, this was squared, so this should be squared as well. Summation of xi squared minus m times x bar times summation of xi. Then I'll just factor the m out. Okay, so m is going to be equal to the summation of yi times xi minus y bar times summation of xi divided by summation of xi squared minus x bar times summation of xi. And now I'll write the subscripts. They were always there, I just didn't want to have to write them throughout. Okay, and this is how I estimate M. Okay. Now I'd like to just go through an example and say something about this equation. Okay. Which is this equation that I have for M does not quite match what's in the book. So what's in the book? So if I want to get what's in the book, that'll be from the book. I'm going to do this to this equation. I'm going to multiply top and bottom by n over n. Then I'm going to distribute that here and here. So I'll have n times summation from I equals 1 to n of yi xi minus y bar times n is just going to be the summation of yi times the summation of xi, like that, divided by, well, distribute the n again, I'll have n times summation of xi squared. The average when it's multiplied by n is just the sum, so it's the summation from I equals 1 to n of xi times summation from I equals 1 to n of xi again. Okay, and that's exactly what's in the book, is this equation right here. Now let's do an example. Calculate my apologies. Okay, and here's going to be our data. Our data is going to have the form of a table, x versus y. This is observational. Okay, and our data is going to have x has values 1, 2, 3, 4, 5. My apologies again. I'm not quite sure why it's doing this. And its value is going to be 3 for y when x is 1, 4.5, 7.5, 8.9, and 11.1. This is a ridiculously small data set, so I apologize for that. Then we need some information, sum of the x's. So summation from I equals 1 to 5 of xi, that is going to be 15. Summation from I equals 1 to 5 of yi, that's going to be 35. Then we need to find the sum from I equals 1 to n of xi yi. That's going to be 125.6. Okay. And now it looks like we have enough information to calculate all of this. So m hat, that's going to be, on the numerator, is going to be 5 times summation xi yi, so that's 125.6 minus summation of y, summation of x. So 35 times 15. On the bottom, I'm going to have, oh, I need one more thing, summation of xi squared. Okay. And that's going to be 55. Okay, so I'll have 5 times 55 and minus 15 squared. Okay, then we just need to calculate this. Okay. So I think we're going to get 2.06 for m. Okay, and now once I have m, I can calculate the equation for b, and that's going to be y bar, so that's going to be 35 over 5 minus 2.06 times x bar, which is going to be 15 over 5. Okay, so we just use this equation right here. Y bar minus m times x bar. I have m, so now I just plug that in. And I think you're going to get 0.82. So our linear regression is y equals 2.06 times x plus 0.82. And I could ask you to do another question, which would be what, my apologies again, what is the predicted value and residual when x equals 3? So let's first do the predicted. So predicted is just plug it into the equation, 2.06 times 3 plus 0.82. Okay, and let's figure that out. I get 7. Okay, so that is my predicted right here. Okay, the residual, which is also known as the error, that's the observed minus the predicted. And that's just going to be, this will be the last time we need to do that. I apologize again. The observed was 7.5. The predicted was 7. The residual is 1/2. Okay, so that is a little bit on the least squares regression line. And we're just going to touch on it in this course. It is one of the most important tools in statistics. Thank you for listening.